Hello and welcome to lesson 29 on concavity and points of inflection. Concavity we kind of saw already in our previous lesson implicitly, but we're going to give it an explicit definition today and solve some problems specifically with concavity and also introduce points of inflection. That being said, before you start today's lesson, please take a moment and complete the practice set, which is an investigation on Google Classroom. This is going to help you get set up for this lesson, as well as to just warm you up and introduce some concepts to you. So now that you've done the practice set, let's introduce what concavity is. So concavity is the rate of change of a function's derivative. So remember, the derivative is f prime of x. And now we're going to see the rate of change of that, which is actually f double prime of x, or the second derivative. And in terms of a graph, the graph and what it would look like, we say that a graph is concave up on an interval if the slopes of f of x are increasing. So that means the rate of change of the derivative is positive. So if f prime of x, so the first derivative, is increasing, which occurs also when f prime double prime of x is defined, so the double derivative also has to be defined, and that the second derivative is greater than 0, then we say that it is concave up. And so showing you what that looks like in an image, this is concave up, so it's opening upward. Now, we also say that a graph can be concave down on an interval if the slopes of f of x are decreasing. So again, if the first and second derivative are defined and f prime of x is decreasing, so this one should be decreasing, so this is less than 0, then we say that the graph is concave down and it's opening downwards. And pretty much what we saw last time was, for example, by determining the end behaviors at times, you were pretty much getting that information, but now we're going to do it more explicitly in regards to concavity. And what we're going to use is the second derivative test. So we've already seen the first derivative test. This is now working with the second derivative. So given a function y equals f of x, which has a critical point at x is c, so remember that's if f prime of c is equal to 0, then we can say the behavior of the curve can be interpreted as the following. So if the second derivative is greater than 0, then we say that the graph is concave up and x is c is the local minimum. And so consider, for example, if it's opening upward, then this point is our minimum, right? And for the second part, same thing. If it's concave down and f double prime of c is less than 0, then we say that this is a local maximum. Now, if the second derivative at x is c is equal to 0, we cannot determine the nature of the critical point. So then we actually have to go back to the first derivative test and analyze it a little bit more. Now I'm going to introduce another definition to you as well, which is our point of inflection. So we saw critical points, which are when the first derivative is 0. Now, a point of inflection is given a function y equals f of x. The point of inflection f of c is if f double prime of x changes signs at x equals c. So if the second derivative is positive and then it becomes negative, then we say that the concavity is changing. So we're going from concave up to concave down, or the other way around. And we say that the point at which this change occurs is a point of inflection. So consider, for example, these two curves shown here. We can clearly see here we're having a change of direction, and same here. And the concavity here is upwards and it's now downwards. And here it's downwards and now it's upwards. So when the concavity is changing, at that point which the change occurs, we have a point of inflection. And at the point of inflection, f double prime of x is equal to 0, or it is undefined. Now, consider the function f of x equals x cubed, which we have seen before. The first derivative of this is 3x squared, and the second derivative is just 6x. Now, We know from here, just looking at the graph, the point of inflection is 0, 0. We go from concave down to concave up. And we can see that f double prime of 0, or maybe let me write this here, is equal to 0. Now, let's look at f of x is equal to x to the power 4. The first derivative here is 4x cubed, and the second derivative is 12x squared. Now, we can also see that f double prime of 0 here is 0, but do we have a point of inflection here? So this part is concave up, and this part is also concave up. So this is not a point of inflection because our concavity is not changing. So going back here, I want to bring your attention to this statement here. At the point of inflection, f double prime of x is equal to 0 or is undefined. So if you have a point and you know it's a point of inflection, for example, based on the curve, then you can tell that the second derivative at that point is 0 or it is undefined. However, if you have that f double prime of x is 0 or it's undefined, that is not enough to say that there is a point of inflection, clearly as we are seeing here. In this case, we do have it 0 and we do have a point of inflection, but here we also have that it's 0, but we do not have a point of inflection. So the statement only works from one side. So if we have a point of inflection, then this is true. But if we have this, we can't necessarily make this conclusion. So it is not an if and only if, it's only one-sided. So that's exactly what you're asked to answer here. So using the two examples above, explain why f double prime of c being 0 is not enough to determine the nature of the point and whether it is the point of inflection. So just putting it in your own words now. And let's look at our next example. So here we're given the function f of x is x cubed minus 3x squared, and we're asked to find any points of inflection and also to state the intervals of concavity. So first consider the first derivative, so just using derivative rules, 3x squared minus 6x. Now, setting f prime of x, so the first derivative is equal to 0, we want to find the critical points. And keep in mind, this is just, or even 3x, if I factor it out, then x minus 2. And so the two critical points are x is 0 and x is 2. Now we find the second derivative, and I'm going to go back and use this one because I don't want to do product rule here. So we're just going to do difference rule, and then we have 6x minus 6. And now if I factor this one, we have x minus 1. And for this to be equal to 0, and this was also equal to 0, then we have one possible point of inflection, which is x is 1. So we're going to test it out, but we don't know for sure that it's a point of inflection just yet. Now, to determine whether it's a point of inflection, we're going to test the values around x is equal to 1. So first we consider x is less than 1 and then x is greater than 1. So when x is less than 1, and again, you're just picking any random value that would work here, so 0 is a good choice. We see that f double prime of 0 is negative 6, so it's less than 0. And this implies that it's a concave down shape. Now, when x is greater than 1, so randomly we're going to pick 2, we see that the second derivative at x is equal to 2 is 6, so it's positive, and this means concave up. So we do have a change in concavity, so now I can then conclude that x is 1 is a point of inflection. And furthermore, we also have, we can say the intervals of concavity. So concave down would be, this is just a dash, not a negative, but this is the interval. So it's concave down when we have negative infinity to 1, and then at 1 to infinity, we have concave up. And so we can say that we have a point of inflection at x is equal to 1, and the point itself we just evaluate is 1 and negative 2. And now I want you to also try applying the second derivative test to find if this is a local maxima or a minima. So to do this, we're going back to the 2 points from our critical points. So remember that the second derivative is 6x minus 6. So we're testing f double prime of 0. So the second derivative at x is 0 and the second derivative at x is 2. So here I get negative 6, which is less than 0. And here I will get just 6, which is greater than 0. So this portion is telling me that I have concave down. And in this part, I have a concave up. So then in this case, this is a local maximum. And again, it's only on a certain interval, a small interval that contains 0. And then on this part, we have a local minimum for x is equal to 2. And I do suggest you try to graph this for yourself and see what this would look like for these 2 points specifically and how that local maximum and minimum shows. So now I'm going to show you a next part, which is going to help us determine this as well. So to do this, we're pretty much doing this, but I'm showing you step by step. So we know that we had these critical points, x is 0 and x is 2. We are setting this table up, which I'm going to show you in the next page how we do this, but this is a sign chart, and you're going to see different variations of this as well. So I'm going to set this up with x is 0 and x is 2 as my two dividers in the line, in the table. Okay, now the spaces in between are going to be the intervals. So here it's x is less than 0. Here is x is between 0 and 2 exclusive, so we don't actually count these 2 points. And here we have x is greater than 0. So first we interpret the first derivative. So in this case, and again, you're just going back to your definition of f of x, which was 3x squared minus 6x. So I'll maybe write that for you. And so for this portion, it is for any values of x less than 0, this is greater than 0. So we say the slope of the tangent is positive. And that means also our function is increasing. Now for this interval, perhaps we pick x is 1. Then we have 3 minus 6, which is negative. So this is negative. And we have that our function is decreasing. And finally, for x is greater than 2, let's say we pick 3, then we have, this is positive. And so we have increasing again. So this is what you've seen before when we were trying to find local maximum and minimum. We're seeing what the, based on the slopes and whether the function is increasing or decreasing, whether it is a maximum or a minimum. So for example, at x is 0, because we go from increasing to decreasing, then we have a local maximum. Now for this one, because it's decreasing and then it's increasing, we have a local minimum. And I already did this portion for you here, but we're pretty much now using the second derivative test to confirm. So we already saw that this is negative 6, and this is 6. And so we do have a local maximum here. And here, when you're asked to find the point, we're just going back to our original function, which was x cubed minus 2, x cubed minus 3x squared. Just gonna double check that. Yeah, there we go. And you're just finding what the point would be. So if we have 0, this is just 0. And at point 2, we have, oh, no, 8 minus 4. And that is our local minimum. So now I want you to think. You have the intervals of concavity, you have the point of inflection, and you have a local maximum and minimum. Is this information enough now to be able to sketch a graph of f of x? And again, it's not an exact graph, but an approximate graph are you able to do so? And I highly suggest you actually try and graph this based on this information and make sure all of these have to be satisfied. So again, just to show you an example, and of course, having a bit of more information, for example, the x-intercepts, y-intercepts would make your graph even more precise, but just based on this value here, so I'm not specifying any scale for here because I'm not figuring out any x-intercepts and y-intercepts, but just based on this, I know that here we have a local maximum, and I will also point this one, -4 there. And over here we have a local minimum. And we also know we have a change in concavity here. For values of x less than 1, we have concave down. So if perhaps somewhere here is our point of inflection, then we have concave down here, something maybe like this. And then we have our change in direction and a local minimum there. Should be like better connected there. There we go. And this goes up like here. And I haven't specified here, again, the x-intercept. Well, this one, yes, but no x-intercept here. And the y-intercept is also there. So aside from this point here, which could be, again, because I haven't specified it, it's approximate. This is a pretty good sketch of our graph. So yes, we were able to use this to sketch a possible interpretation of this graph. And even just based on here, for example, I'll show you one more possibility. You can even expand this, like do vertical stretches and compressions. This could also be a possibility based on just this information. So if I didn't tell you what the function was and I just told you these pieces of information, you should be able to approximately sketch a graph. So this is the sine table I was mentioning. So a sine table, or it's also called a sine chart, is a mathematical tool that can help us determine intervals for which the function or its derivatives are positive, negative, or zero. So these can help us determine increasing or decreasing behavior using the first derivative, concavity using the second derivative, and key features like critical points and points of inflection. So when the first or second derivative are zero. So how we create a sine table, and it's pretty much what we've done here, but this is the full explanation of it. So you definitely want your first derivative to determine increasing and decreasing behavior. Based on that, you can determine your critical points, and your critical points will be divisors for your table. And also based on that, where the function is undefined, perhaps your asymptotes there, those will also be used to divide your table up. Then we find the second derivative, and this is going to help us determine concavity. So we're just testing the second derivative based on those intervals, and we can use that to find our points of inflection. So yes, we find where it's equal to 0, and we have possible points of inflection. Then we test we test the first and second derivative for those intervals that we've created based on critical points and points of inflection. And again, these are used to divide your table into the intervals. So for example, if we have A and B, which could be critical points or possible points of inflection, and this is how our table would be split up. And then you are building your table, and I have included a template here for you. So this table here, so you can just adjust these, add more columns if you need, and these are the values we're interpreting. So the sign of the first derivative, and based on that we have increasing or decreasing, and signs of the second derivative, and based on that we have concavity. And so remember, when the first derivative is greater than 0, we have increasing. When it's less than 0, we have decreasing. When the second derivative is greater than 0, we have concave up. And when it's less than 0, we have concave down. And once you have this table set up, you may be able to start, or you can draw a sketch of your graph so far based on this information. And as we work through these next problems and in future lessons, you'll see that I don't always use all parts of this. So sometimes the table is modified, or additional information is added, and it's based on what you need for that graph, and it'll be based on case to case. So you'll see what piece of information is useful to you. So let's test now here. We have the function f of x is x to the power of 4 minus 4x cubed. So first I'm finding the first derivative here. So I factored it out already. And we find the critical points are x is 0 and x is 3, which I'm getting from here. This is x is 0 and this is x is 3 by setting f prime of x to 0. Now, I also found the second derivative for you here. So it's 12x squared minus 24x. And again, always use that expanded form just so it's easier for derivative rules. Now, possible points of inflection here are x is 0 and x is 2. So now I'm setting my table up and I already have set it up for you, but I'm going to go through it and explain each part. So here is x is 0, which is actually both a critical point and a possible point of inflection. Then I have the second possible point of inflection here, and finally my next one, which is the critical point, x is 3. And so these intervals here, this is of course x is less than 0, this is x between 0 and 2, x between 2 and 3, and x is greater than 3. Now, I have my first derivative and second derivative there as well, and I'm going to determine what the signs are. So just looking at these values, and again, you're just, or maybe even these ones, you're just testing out values. So here you might pick x is, for example, x is -1. Or in this one, we might pick x is 1. This one is a little bit trickier because you don't have an integer there, so just maybe 2.5. And here, x is 4. So possible points, and you're just testing it out. And you should see that we get a negative derivative here, which means decreasing. And the concavity here is positive, so concave up. Now, if you continue this, we have all of these are decreasing. So pretty much from x is less than 3, we have the function is decreasing. And then for x is greater than 3, we have increasing. So we have a point here that's going to be important. And here we have our concavity. We see that we have a concave up, a concave down, and 2 concave ups. So we have a change in concavity here and a change in concavity here, which is exactly what we were seeing from our points of inflection. So in fact, these two are both points of inflections based on the fact that the concavity is changing. Now, for x is 3, we do have an interpretation here because the function is decreasing and then it's increasing, then it is a local minimum. But we could also double check with the second derivative, so f double prime of 3. And remember, it's 12x squared minus 24x. And you should get that it is greater than 0. And again, we see that from here itself. So that means it's concave up, and our graph would look like this. And so yes, we do have a local minimum. And so I've summarized here all the information from this table. So we have the intervals of concave up, we have the interval of concave down, and we know that at x is 0 and x is 2, we have a point of inflection because the concavity changes, not necessarily because the second derivative is equal to 0. Although that did help us figure these 2 points out as possible points of inflection, the fact that the concavity changes is what actually determines that these are points of inflection. And at f of x is 0, so as we saw here, because the change, there's no change of sign, so it's decreasing and it's just decreasing, then it is not a local maximum or minimum. So it's, for example, as we saw in the graph I sketched for you up there, could be something like this, where here you are having a change of direction, but that point itself is not a local maximum or minimum, but the concavity is just changing there. However, at x is 3, we do have a change in sign. We're going from decreasing to increasing, and we also check the second derivative. So we have a local minimum at this point, and we can also determine the local minimum based on the function, which is 3, -27. Also here, the reason why it's important to add this is because f of x was a critical point for us as well. So it was also a possible candidate for a local maximum or minimum, so that's why it is important to check that as well. But clearly we saw that it is neither a maximum or a minimum. Now let's make connections from above to the graph. This is what the graph looks like. So here we have x is 0 and x is 2, which are our points of inflection. So clearly here you can see we're going concave up and it's concave down. And now here we're from concave down, we are going to concave up and we continue and it stays concave up. Now, this is that point we were just saying, point 0, 0. Clearly we see that although it was a candidate for a critical point, it is not a minimum or a maximum, depending on like the interval that we're considering. And so it is just a point of inflection for us. However, this point, 3, -27, is a local minimum. And we can see that all values of x from left and right are greater than -27, so it is a minimum. And we checked algebraically using second derivative test as well that it is a local minimum. Now let's look at this next example. This is also our last example for this lesson. So consider the function f of x is 1 over x squared plus 3, and we're asked to determine the points of inflection. So I've written this as a -1 exponent, so I can find the first derivative. So remember power rule here, x squared plus 3, we get -2. And then we also have to find the derivative of the internal function using chain rule, so just 2x. Now, this is, you can either think of it as a product rule as is, or you can change it to this rational function, and then use quotient rule. But I just use product rule here. So we are finding the second derivative. So this is just finding the derivative of each term, and simplifying that, we have this expression here. So here, I've just rewritten these as fractions, and I found common denominators here because I wanted this term here, which is 6 times x squared minus 1 over x squared plus 3. And the reason why I did that, because we wanted to find points of inflection. And to do that, we want to find f double prime of x is equal to 0. And I hope you can see from here, that looks scary to approach. And even here, it's not enough. So that's why you have to do some mathematical and algebraic manipulation to find this expression here. And this I can actually now solve for the derivative, second derivative equals to 0, because this is pretty much, we're only, for this to be 0, we're looking at the numerator to be 0. Especially because considering the denominator, x squared plus 3 is greater than 0 for all values of x in R, because x squared is greater than 0 and we're just adding a 3 to it. So now considering the numerator, x squared minus 1, and again, the constant isn't going to contribute anything here. So this is equal to 0 when x is 1 or x is -1. So now, I included this here as well, just a different way of showing the sign chart. And this is now a simplified sign chart because I'm not looking at the first and second derivative, or sorry, the first derivative here and intervals of increasing and decreasing, because I was only asked about points of inflection. So I only care about concavity. So of course here we have a possible point of inflection, and same with here, but this part doesn't get filled in till after. So I have to do these three first. And so pretty much what I've done is we consider x is less than -1, x is greater than 1, and then the interval in between. And of course, we know at these 2 points, the second derivative is equal to 0. So these are for sure possible points of inflection. And here, because we have a concave up, concave down, and then concave up, then they for sure are points of inflection. That being said, if you had concave up, then this would just, you can just leave this empty. It would not be there because you do not have a point of inflection. But in this case, it is true. And we can see this based on the graph as well. So at x is -1, and although it is stretched out, we do still see that this part is concave up and this is concave down, and then we have concave up. And so, of course, those are points of inflection because concavity is changing. And so That was another characteristics of our graphs, concavity, and it's especially important when we are trying to sketch graphs. It's important to know what our points of inflections are, and based on the second derivative, we can find concavity to get a nicer or a more accurate sketch of our curve. And that is a wrap on this lesson. If you have any questions, don't hesitate to reach out. And as always, check Google Classroom for additional tasks. And I will see you all next class.